Okay, so let's continue to talk about this continuous inversion problem. So I guess the problem setting is, as we just discussed, is actually quite clear that in general, we have input basically this A1, A2 to AN, and we want to compute the number of inversions. So it's basically this problem. So for this problem, you can actually see this problem is, of course, can be solved in polynomial time. You can just like do like a brute force way. Brute force, we just like check all pairs. I mean, the cost of this algorithm is basically n choose 2, which is n times n minus 1 over 2, and this is O(n) squared. So similar to the case of merge sort, we basically want to have a better algorithm. And of course, as you can imagine, and maybe you can also imagine that this kind of continuous inversions, this is more like a quantitative version of the sorting problem. We would actually want to count what is the number of this kind of inversion pairs. So we can imagine that it is also quite natural. We can consider like a divide and conquer strategy. Yes. So what is the divide and conquer strategy here? So for the divide here is of course also quite straightforward, and we just separate the list into two pieces. And I guess, of course, you can clearly see that this is also the same as the sorting problem, just cutting the middle. And cutting this is really something quite easy. So this causes O of 1 here. And then it is basically the conquer part. And for the conquer part, we just recursively count inversions in each half. And basically the cost of this step is basically 2 times t of n over 2. Okay, so the remaining thing that we need to be specifically careful about is the combined part. So basically for this combined part, we need to count inversions. Basically where A and AJ are in different halves. So basically, due to the recursion, we have basically in the conquer part, we have solved the two sub problems. So the remaining thing about this merge or combine is that we need to be careful to count the inversions where AJ and A and J actually one in the half part, left half, and the other in the right half. And basically, this is the part that we need to take a specific care with in different halves. And actually, we need to return the sum of all three quantities. So that is basically a number of inversions in left, and actually number of inversions in right, and also number of inversions between left and right. I guess this is relatively straightforward. So as I just mentioned, for instance, for the example of the merge sort, actually the intricate part and actually the part we need to be careful with and actually a little bit sophisticated is that we need to be careful with the combined part. So here we can imagine, I mean, well, we already have like counted the inversions the left part and also the right part. I mean, like the brute force way, it's still like check all the n over 2 times n over 2 equals to n over 4, n to the 4 over 4 pairs between left and right. And we don't need to make any further calculation because already this step, I mean, it's already n to the n squared over 4. So this is n squared. Actually, no better than direct brute force. So if there's only one step of combine is already basically the same as the original, the brute force one, there's just no sense to consider divide and conquer algorithm. Here we should really set actually a higher goal here, because probably this is not the best way to do the merge here. So the goal here is actually the combine of the inversion counting problem. Can also actually be done in linear time. Yes. So basically, we need to think about how we can actually give a good strategy for this counting inversion problem. So as I just briefly mentioned, so intuitively, you can imagine this is somehow like a quantitative version of the sorting problem, because for like a sorted list, the number of inversions is just 0 here. So maybe you want to like utilize this kind of strategy, and basically we have basically introduced this merge sort algorithm that actually for the merge sort, the merging step is actually only taking linear cost, and actually overall the cost of the merge sort algorithm is O of n log n. So this is actually quite good, and in general, maybe we want to utilize this fact that sorting is good. Actually, maybe we can use this sort as actually like a basic, basically like a fundamental step upon this inverse, basically counting inversion problem. So basically, we say that to achieve this, we consider sorting and actually counting inversions at the same time. So how do we actually want to do this? So here is that basically recall that we have actually rigorously written down an algorithm. So basically this algorithm from merge. So basically we are going to make a further modification. So here we only know how to merge, but maybe hopefully along this way of making a merge here, you can also count the number of inversions, and actually that will be the ideal case. So let's actually just imagine that how we are actually going to do this, and maybe let's actually do this by example. So we consider example, maybe for instance, we have like, for instance, like 6, 1, 12, maybe also like a 4, 10, 2 here. So in the divide and conquer here, we are actually going to make a division in the middle. And actually here we have like a 6, 1, 12. And here we are actually going to have like a 4, 10, 2 here. So in the conquer part, we basically know that actually the number of inversions, and actually for this 6, 1, 12, you can clearly see that the number of inversions is actually, let's maybe actually do this. So you can clearly see that basically for this part, it's basically 1, because the only pair of inversion is the 6 and 1. Because 6 is smaller than 12, and also 1 is smaller than 12. But for the second part, for this 4, 10, 2 here, so the number of inversions is actually 2 here. Because actually we have the pair, basically this 4 and 2, and also 10 and 2 here. So if we only have this, this is probably not very helpful enough. But here we consider basically a merge and sort. So one thing that is actually a key observation here. So sorting in left and right is not forms inversion pairs between left and right. Okay, so what do I mean by that? So just imagine that here it is sorted. For instance, like 1, 6, 12, and here it is like 2, 4, 10 here. So if we just like at the original, we look at this. We look at the inversion pairs here. So you can clearly see that, for instance, at the very beginning, 6, 4 is actually an inversion pair. But actually, no matter you actually sort this, I mean, for instance, here, the 6 is sorted here, and actually the 4 is sorted here. The left part, I mean, no matter how you sort this, is always to the left of the right part. I mean, the corresponding index is always going to be smaller than that. I mean, no matter how actually you are going to influence this, I mean, for instance, no matter 6 is in this place or 4 is in this place, or maybe 6 is in this place or 4 is in this place. I mean, this does not influence the inversion pairs. And actually, this is a very important observation here that we make, is that sorting inside each part is actually not going to influence the number of inversion pairs along this. As long as you have, I mean, maybe for instance, you have an algorithm, and actually we call an algorithm later we will see. We will say this is algorithm. We call it a merge and count. Merge and count and left to right. So as long as your algorithm can give a correct return about like the number of inversions in the left part and the right part respectively, and you have a good way of merging between left and right, then actually you are good, because I'm actually sorting does not really influence the inversion pairs between left and right. So is this key observation clear to you? I guess this should be probably relatively straightforward, I guess. So maybe the only remaining thing that we need to talk about is actually how we want to do the merge. I mean, how actually we count the inversion pairs between left and right. So we similarly, we use this kind of strategy that where we have a pointer here. Where we have a pointer here. So basically, let's think about how we want to do this. So basically, because we are actually doing like a merge and count. So for the subproblems, if those numbers are sorted, your final output should also be sorted if you want to keep this merge and sort this kind of function. I mean, if you want to always keep this. So as long as you merge the small problem to the large problem, you also need to give like a sorting of these items. So let's basically also have these pointers and actually consider like a strategy of actually merging all these elements. So basically you have a 1 here. And actually here you have a 1 here. And for the left part, you have a 1 here. And for the right part, you have a 2 here. So we clearly see that this 1 does not incur any inversion here, because 1 is smaller than 2. And 2 is actually already, because it is already the smallest element in the right-hand side. 1 is smaller than 2, 2 is further smaller than 4 and 10 here. So actually this 1 does not incur any inversion here. So we add this 1 here, and as basically what we discussed for the merge sort, we delete this 1, and actually we move to the pointer to the next step. So here it becomes more interesting, because here, I mean, the 6 here is actually larger than 2. So we see that basically for this problem of inversion counting, if some atom in the left-hand side is larger than the right-hand side, you actually got a signal that there must be an inversion pair. But we actually need to be careful about how many inversion pairs do we actually encounter here. So here, specifically for this 6 here. So in particular, we need to think about actually how many pairs that actually incurs. So specifically because 6 is larger than 2, the item that we delete here is 2 here. So we actually add a 2 here. So, but we need to be careful with this 2, because specifically here we are deleting an item at the right-hand side, and actually this 2 offers you something. So specifically, we keep in mind that actually on this 6, 2, and actually the 12, 2, they are actually inversion pairs. So let's maybe assume that we have a count inversion. So here, for this 1 here, we are actually quite safe to just write a 0 here. But for this 2 here, basically added from the right-hand side. So we know that because we have a 6 here, 6 is larger than 2. And actually, because 6 is already larger than 2, and the left-hand side, it is sorted. So 12 must be larger than 2. So we are pretty aware of this, and actually we can have a +2 here. And so this is the next step where we move to the 4 here. So for this 4, we make another comparison. I mean, we compare the smallest on the left-hand side and also smallest on the right-hand side, basically 6 and 4. And clearly we see that 6 is actually larger than 4. And actually we're going to delete this 4 again, and we add the 4 in the sorted list. So in this sorted list, basically we see that because 4 is smaller than the 6, and actually because the left-hand side is sorting, as I always mentioned, it also must be smaller than 12. So the number of inversions that actually it also incurs is actually also 2 here. And then we move to the 10. And 6 is actually smaller than 10, and actually we are good with that. We just write the 6 down, and actually we want to be cautious because maybe you want to think about, okay, 6 is larger than 2, and actually 6 is larger than 4. But actually it is already counted. So the logic here is that we add this. Maybe let me use a red color. Add this. Then maybe not, but according to which is added in the sorting. So we basically don't want to, this 6-2 pairs, it is already counted in 2 here, and we don't want to already counted when we add the 2 here. So we don't really want to count this for twice, then actually this will ruin everything. So basically when we added the 2 here, we actually added here, and then we write down like a +2 here, and 4 here, we write down a +2 here. And after that, for the left-hand side, we don't need to further worry about this, because actually 6 here is actually smaller than 10, and actually we are good with that. And then the pointer moves to 12. And actually 12 here is actually larger than 10. And actually here we're actually going to have another +1. And actually this finishes because the last item is just 12. Because here after deleting 10, we already moved to the end of this array in the right-hand side. So we just write everything down. There is no further thing that here we want to add. So a number of inversion here that we basically we got from this merge part is actually 5 here. So basically the total number of inversions is basically this 5 from merge. And also we need to plus 1 from left. And also we need to plus 2 from right. Goes to 8. And this is actually the total number of inversions in this original. Is this clear to you? Okay, so I guess this intuition here is relatively straightforward. And actually in this algorithm, you can clearly see that this cost is actually O of n here. But I think still, for you to better understand this algorithm, and I think it's still very important for me. Here, although the merge sort idea is relatively straightforward, but actually I write down the algorithm here. So I think still maybe it's a good practice for me to actually write down this merge and count algorithm maybe for the next page. Yeah, I think maybe this is going to be helpful for you to understand like how we are actually going to do things rigorously. So because here we are actually doing counting and basically doing sorting and actually counting inversions at the same time. So we are basically actually just follow very closely to the merge sort algorithm. Basically, we are still going to have this pointers ij equals to 1. This ij is basically still this ij here. But here we are actually going to have another register here. So we have another register we call it counter. Originally, it is initialized to be 0 because originally we don't have any inversions. We just need to count them throughout. So basically, the algorithm is similar to the above algorithm. So we still have this while condition. So while we have not finished the pointer. So while I and j is smaller than n over 2 plus 1, and actually if left I is smaller than right j here. So if 2 entries are equal, for instance, in the preference of songs, in this kind of like recommendation system, there's going to be no equal things. Or maybe there are just like cases, maybe for instance, I like apple and banana both. I cannot really distinguish them. In general, if they are like same value, we just don't regard this as like an inverse order. I guess this probably is going to make sense. So as long as the left-hand side is smaller than or equal to the right-hand side correspondingly, we just add left I to merge I plus j minus 1, and actually accordingly increase the I here. So basically, this is the easy case, and basically recall what we discussed above here. We actually do a very careful calculation here. Basically, we count the inversion when the left-hand side is smaller than the right-hand side. So basically, we need to be very cautious about the next line. So the next case, as I just mentioned, is the case if left I is actually, I think this should not be an if, but actually else. I mean, if this if is not true, then else it simply means that the left I is actually larger than right J. We just add right J to merge I plus J minus 1 J update to J plus 1. But this is not ended. We must be careful here because this is the place where we are actually counting the number of inversions here. And actually, what is the number of inversions here that we actually encounter here? So we are actually at the currently assume that we add a place at I here, and actually let's do the 4 here. So we are at a Jth place here. So the fact, a key fact that we are actually maybe let me actually leave a little bit of space here. So I think maybe I can say in this. So note. So basically, when we are in the line left I is actually larger than right J. So basically, in this case, we are aware that left I is larger than right J. This is just our assumption. But we must have the case that right J is actually larger than or equal to left I minus 1. Because that is the case where your pointer is currently at this place. So here your pointer is currently at a 6. It is not at the place of 1 here. So just imagine how you actually run this algorithm. So if your pointer is currently at a 6, it must be the case that your pointer moved from the previous place to the current place. And how it moved from the current place to the current place, sorry, to the previous place to the current place is just because you must have this to be true. Otherwise, your pointer should not currently be at the ith place. So, or maybe for instance, at this current example, you can clearly see that, I mean, if your pointer is currently at 6, I mean, you must have the case where 1 is smaller than 4. Is this clear to you? Just imagine how you actually run this algorithm, because if your pointer is currently at 6, I mean, if the previous element, I mean, if 1 is larger than 4, your pointer just shouldn't be at the place where it's currently at the 6, because it shouldn't have moved it. So this is a very important observation that we actually made here. So, and actually this gives you a direct answer to basically how many we should add to the counter here. So basically here we are at the th place. And we know that at the other places, from the first place to the I minus 1 place, it is actually smaller than the current pointer at the right-hand part, basically at the current J. So we know that basically the thing that we need to add here, basically the counter here is basically going to be counter plus n minus I. So why is this the case? So this is basically from the f to the n. Because n minus 1, it is actually smaller than the current item in the right. That's basically the item you are adding just here. And actually, the ith is actually larger than that. And basically, because the left-hand side, it is sorted. If the ith element is larger than the current element you added from the right-hand side, so does the I plus 1, I plus 2 until n. And that is exactly the number we need to add to the counter here. And that is basically the reason why we actually add like a plus 2 here. And actually a plus 2 here. Because basically here, actually, no matter you are actually in this pointer at the 2 and actually at the 4 place, the plus 2 here is because basically you have 2 elements here. And basically here, the 1 here is that basically when the pointer is at 10 here, and actually the pointer is at 12 here, you exactly have 1 element, it's basically the 12 here. And that is the exact reason, basically, the correct value that you need to add to the count of the inversions. So is actually this red line clear to you? Basically, how many we need to add to the counter here. So any questions? Okay, so this is basically the most important line of this algorithm, actually the most significant difference compared to only we sort the algorithm. So basically, let's just finish the rest of the algorithm. And I guess the remaining part is probably quite straightforward as we discussed about this sorting algorithm. So basically, if this pointer of I move out of the boundary and move to n over 2 plus 1, we just append the remain of right to the end of merge. And actually, on the other hand, else. And for the else case, that is going to be j equals to n over 2 plus 1. We are, of course, going to append the remain of left end of merge. And actually, this not only gives you actually a sorting of this algorithm, but also give you the counting of the inversions. So I guess this basically finishes the discussion, basically a very particular point about like how we are actually run this algorithm, and we count the number of inversions basically by this argument here. Basically by this argument, actually this observation that we made. So is this clear to you? So sure. Oh, sorry. Sorry, are you talking about this line or sorry, what is? Oh, sorry, right. Sorry, yes, yeah, thanks for the suggestion. It's basically, I think I probably made a slight mistake in my preparation of the lecture. It's basically because the length, I mean, it's basically the length. I mean, the length here is n over 2, and also, and also the length here is also n over 2. So basically here, yes, it should be n over 2. Yeah, thanks for the correction. Let me actually mark this so that I didn't teach it wrong next year. Okay. Any other questions?
I was wondering why I gave this N2 possible, not just N2.
I mean, at the boundary case is I mean, this is not so important. It's just like a way of writing this rigorously. I mean, it's just like, for instance, here, I moved I have this n over 2 plus 1. It's just a case where, okay, I ran out of this left array and just like move it out of this. I mean, you can stop when it is n over 2. It's just a way. I mean, when you just program everything, it's just like some details that is up to your favor. So it's not so important. Any other questions? Okay, so if this is clear, I think we basically finished the discussion of arrays, basically this merge sort and a very similar problem, but a little bit more intricate problem of counting inversions. So next we are going to, because in general, we want to talk about algorithm design, and I guess you students are from like a very different background. I guess in this course, we are probably going to introduce algorithm for different perspectives. For instance, in the last lecture, we also, for instance, introduced something from information theory, basically this Hoffman codes. So this is basically we're actually switching the topic alongside, but we want to focus on the idea of designing the algorithms behind. So the next case that we are going to discuss is actually something from geometry. So next example we are going to talk about is to finding the closest pair of points. So of course we need to define this. So problem is that we are given n points in the Euclidean plane. I mean, two-dimensional Euclidean plane. So we want to find a pair. With the smallest Euclidean distance. Between them. So specifically, we can say the endpoints. Assume them to be like x1, y1, x2, y2, xn, yn. Actually, here for all the coordinates, they're going to be real numbers. And the Euclidean distance I mean, for instance, between like xi, yi, xj, yj is basically the distance in L2 norm, which is basically the square root of xi minus xj squared plus yi minus yj squared. So is this definition clear to you? Okay, so we can imagine that this is actually a very fundamental problem. So in general, I mean, for this kind of problem where you have vertices, I want to consider like the pairs where actually they're the closest between. Basically, for instance, this has wide applications in. I mean, you can imagine that this has wide applications in graphics. I mean, maybe also computer vision. And such kind of functions, I mean, consider like the closest pair. So this is also, I mean, in big data, I mean, you can also imagine in big data, you have a lot of data points, and maybe you want to consider some kind of cluster, I mean, and also whether like a point is close to each other. So this is also a very important gadget that you will need to use, for instance, in nearest neighbor search. And also, I mean, in our class, we talk about minimum spanning tree in the graph sense. And actually, there is, for instance, there are also like Euclidean a minimum spanning tree, and also in general, like geometric data structure, etc. So I mean, this is just a very brief discussion, but in general, this kind of finding the closest pair of points is a really important problem that is used a lot in different applications. So here, I mean, we are talking about algorithm design, and we just talk about this very abstract problem of finding the closest pair of points. So let's think about like the good algorithm for this. I mean, similar to the sorting problem, I mean, also similar to the count inversion problem. I guess you can directly imagine that the brute force way. The brute force way of this algorithm causes still like you just like try all the pairs. I mean, it's just like for the star. I mean, for the star equation, you just compute for this value for all the pairs I and j here. You can clearly see that the causes, this problem can be solved within cos O of n squared. But are we actually satisfied with this? So I guess maybe we want to be actually more thoughtful, and in general, maybe hopefully we can improve this. I mean, also for this closest pair of points problem. So let's take a quick look, for instance, consider like the 1D version. So what is the 1D version? So one-dimensional case. So that is basically you have like x1, x2, and xn. So basically you want to compute the smallest xi minus xj. And actually, of course, I not equal to j. So maybe you can quickly think about this. I mean, can you actually do this better than O of n squared? Yes, yes. As you can clearly see, we can actually give like O and log n algorithm. We just sort. So we sort, and maybe for instance, without loss of generality, we can assume that x1 is smaller than x2, smaller than xn. And the output, and of course, this is going to, as we just mentioned, for the merge sort. So this part, the cost is O of n log n. The output is simply then the minimum of x2 minus x1, x3 minus x2, until xn minus xn minus 1. So I guess this 1D case should be relatively straightforward. Because after you just consider, I mean, like points on this, maybe like an axis here, like this. So it is indeed important you want to sort this. And after you sort this, we just like compute the value of these consecutive segments. And I guess after compute all these consecutive segments and taking the minimum among those, we will definitely solve this closest pair. So I guess this 1D case should be relatively straightforward, but I guess for the 2D case, you can probably imagine that this is, I mean, this just brute force sorting strategy is not going to work directly. And maybe you want to have, I mean, you need to introduce some new idea here. So here, I mean, for our discussion here, I mean, to make the presentation clear. So without loss of generality, we assume no 2 points have the same x coordinate. So this is assumption without loss of generality. So actually, having this assumption, maybe I mean, after I wrote this down, you can think about like how, for instance, we want to use the divide and conquer strategy, how we are actually going to do this. So it is still that we are actually going to somehow divide the problem, maybe for instance, into 2 parts. And actually, hopefully you can recursively call the 2 parts and have like a clever strategy that you can merge. And actually, what is a possible strategy that you can make the division? So specifically, I mean, for this kind of problem of making the closest pair, I mean, if your division is actually, for instance, like really dismantled into several parts, then it's probably quite difficult that you can figure out, I mean, how actually this is going to reveal the closest pair. So as you can imagine that a natural strategy that we can make the divide here is that we draw a vertical line. I mean, here as the normal practice, so the horizontal axis is the x-axis and the vertical axis is the y-axis. So I draw a vertical line L so that n over 2 points on each side. So here for the ease of our discussion, we can also, without also generality, we assume that n is a power of 2 here. So we just draw a vertical line L, and also based on our assumption that we assume no 2 points have the same x coordinate. This is just for the ease of our life, and actually this is not so difficult to be released. But actually, without also generality, we assume this, and actually assuming this, we know that we can actually draw a vertical line L so that 1 over basically n over 2 points are on each side. So this is actually doable in time O of n log n by pre-sorting all on x's. So, I mean, we know sorting. I mean, sorting is basically something we are familiar with. We just learn how to do a sorting cos of O n times log n here. So we just, without loss of generality, assume that all the coordinates, I mean, they're x's, they're actually sorted. And maybe, for instance, like x1 is smaller than x2, etc. So basically, this is something we can feel free to take into granted. So basically, we can maybe assume this is like an output. This gives an output. Output basically a line L. This L is basically x equals to x star, where x star is between the n over 2 and n over 2 plus 1 in x coordinates. So the conquer part, so this is it's just recursive calls. So we find the closest pair on each side. On each side recursively. And the combine part is, of course, we need to have a good strategy to actually combine the left part and the right part with 1 point in each side. And basically, to figure this out, we just need to, this combine, to find like the closest pair of points, between left and right. It's just equivalent to the problem of finding the closest pair with 1 point in each side. And actually, for the conquer part and also for the combine part, so basically, we find the closest pair in each side, the left-hand side and also the right-hand side. And basically, we have two values. And basically, for the combine part, we also have another value. So basically, what we return is basically the best of the three solutions. So like the left and right and the merge. So maybe let's, for instance, maybe let's draw like some example here. Maybe let me actually draw here. So here you can probably see that I think I'm actually drawing like 12 vertices here. And actually here, let's say n equals to 12. So in this case, basically for the left-hand side and for the right-hand side, if we make the divide and conquer, so basically we are going to make a division here. So basically the left-hand side has actually 6 vertices and the right-hand side also has 6 vertices. So if you run this divide and conquer idea, you will, for instance, like the left-hand side, you can clearly see this is really like a closest pair. And for the right-hand side, this is actually the closest pair. And for the merge, between left and right, and since that probably this is like the closest pair. And what you need to return is that basically you need to return the best of the three solutions here, and actually you need to check which is the smallest one. This is the L. So this is the L here. So is this clear to you? Basically, this description of the divide and conquer idea. Okay, so it seems that the remaining question here is that basically the combine. So the combine seems to take theta n squared cost in the worst case. So why am I saying that? So you can just imagine there is some maybe a little bit weird case where you have like an L here, but all the points, they are really close with each other. What if we encounter such kind of case? This is probably really going to be a little bit embarrassing. And this is basically, the observation is based on that check all pairs. Excuse me. Check all pairs take actually theta and squared cost. So here, I think maybe you can probably see that this situation is a little bit more evolved, because if we only like, roughly speaking, taking like the vertices close to this line L here, all the vertices can be close to your line. And this is really not so straightforward, and maybe we need a better strategy. Instead, actually, we want to check all the pairs between. Maybe this cost is just like n over 2 times n over 2 is just like n squared. This is just so expensive, and maybe we need like a better strategy to do the merge here. And actually, the main question is that how do we improve upon this? So is everything clear so far? Yes. So this is basically, I think, something we need to like a clear introduction. So recall here, if you only look at the merge, this is probably not helpful enough. For instance, in the merge sort and also the counting inversion problem, we really utilize the structure of the left-hand side and actually the right-hand side. And here for the left-hand side and for the right-hand side is that basically due to this recursive clause, we actually know the shortest pair, the closest pair in the left and in the right respectively. So this is basically something maybe we want to utilize, and basically this minimum value, and hopefully this minimum value in the left-hand side and right-hand side can provide us some information that we can utilize. So next, we are actually going to make observation here. So the observation that we are going to make is that maybe, for instance, let's denote delta to be the minimum of the two recursive calls in division. Then you only need to consider those points within delta of line. And I think we call this the delta strip. So basically, we know that we have recursive clause to the left and the right, and basically we just know this delta to be the minimum. So we have this L here. And basically we have this delta. So assume that you have a point here. It is outside this delta strip. Even if you have like a point super close to this L, from the left-hand side, this is not going to actually bother you because the distance between your left-hand vertex and also right-hand vertex, the distance should be at least delta. I guess this should be clear to you, I guess. And that is the reason, as long as you have like a vertex outside this delta strip, so this is really not going to bother. So any question here? So this is actually a good start. And actually this tells us that we have something to focus on. So the strategy is that we sort points in the delta strip by their y coordinate. And actually, let's denote SI, the point in the delta strip. Smallest. So here we are really actually looking at things inside, and basically we want to have a good sense about, for instance, you have points, vertices inside this delta strip. What are actually going to be the case? You can, roughly speaking, you cannot have like super close vertices like this. So why is this the case? Because we have successfully run the algorithm on the left-hand side and actually the right-hand side. And we know that basically we have called this delta to be the minimum of two recursive calls in division. You have two vertices super close like this. This looks like much smaller than the delta here. This is just an issue here. You just cannot have vertices that are actually super close because just due to the definition of delta here. So you are probably going to imagine that your vertices here, they should actually have some distance here. Although, between the left and the right, there can be super close vertices. But inside the left strip and the right strip, the distance should be relatively sparse, intuitively. So I think I probably only have 1 minute for this class and we need to take another 10-minute break. But I think I'm actually going to turn this into a rigorous result. So a key observation that I'm going to show in the next hour. Key observation. So if the distance, if the indexes differ by a lot, so if I minus j is larger than 12, then the distance between Si and Sj is actually at least delta. So basically, we are just going to turn the intuition I just mentioned above to something rigorous, and basically like a constant here, and basically we want to make sure that as long as they're coordinate, I mean they're sorting, I mean the sorting according to the y coordinate, and if the corresponding index differ by at least 12, then basically we are good. Actually, we don't need to worry about such kind of pairs. Okay, so let's take a 10-minute break and let's come back at 10 or 5.